Hey guys, Miss Pipel here. Today in this video we're going to be looking at periodic trends, or the things that vary in a specific pattern on the actual periodic table. So if you think back to the alien activity, we had a key similarity and then a varying trait for both going across the row and down a group on the periodic table, or on your periodic table of aliens. So we're going to kind of equate that to our actual periodic table. So the key similarity that our elements in the same group have is your number of valence electrons, right? And then that oxidation number that goes with that. We'll talk about that in class. In the periods or the rows, okay, we want to think about that they have the same outermost energy level for their electrons. So things in the same group are all going to end with a very similar electron configuration, whereas things in the same period are going to end with their electron configuration on the same energy level. For example, the second energy level or the third energy level, and so on. So want to keep that in mind as we go through this video. Okay, so there are three trends or three properties that vary in a specific way across your periodic table that we are going to be looking at in this unit. The first is ionization energy, or what is sometimes called the first ionization energy, which is the energy needed to remove an electron from an atom. And we generally just think about removing the first electron. Okay, the higher this number is, that means it means it's harder to actually pull that electron off. Okay, so that atom has a stronger hold of the electron. Okay, atomic radius is just what it sounds like, the distance from the nucleus to those outermost electrons. Obviously, we can't see atoms, but there are some ways that we can measure this. Obviously, a larger number here means a bigger atom. And then the last thing is electronegativity, or sometimes electroaffinity. So this is how attractive an atom is to other electrons when it's in a bond, and that's kind of the key part there. It's talking about when an atom is bonded to another one. The higher the electronegativity value, the more attractive or the stronger hold, again, an atom will have on its electrons, or other electrons in the bond for that matter. So let's look at the patterns about these different properties. Okay, so the pattern we see for atomic radius is as you go down a column, the atoms get bigger, so that atomic radius value increases. And then actually as you move to the left, okay, your atomic radius also increases, okay? Or you could say it decreases going to the right. Okay, either way, but if you're talking about going down, the atomic radius increases, going right, atomic radius decreases. So let's think about why that is. As you go from top to bottom on the groups on the periodic table, we said that they have like the same number of valence electrons, but the energy level that those valence electrons are in are getting further and further away. We have more and more electrons we have to fit, more and more principal energy levels that have to fit in that atom, and so that will generally just make your atom bigger. Okay, going from right to left, we're talking about now we're on the same energy level, right? So as you move to the right, you're adding one additional proton, and remember, our positively charged protons attract the negatively charged electrons. That's going to be a key thing here. The things that will affect that attraction are, one, how far away they are, and two, how many or how strong that nucleus is. The more protons is like adding more muscle. So more protons means that those electrons are held on tighter and are held on more strongly, which means that the protons will pull them in a little closer to itself, making that atom a little bit smaller. So more protons, again, means more pulling power, and so electrons get closer to the nucleus. So that's your trend for atomic radius. Okay, we also have talked a lot about ions, and so that's kind of when we're dealing with gaining or losing electrons, right? So cations is the name of a positively charged ion, which we're going to talk more about. But what we need to know is that those, since they lose electrons, they will get smaller, okay? And anions, which are negatively charged because they gain electrons, are going to be larger than their original atom. And that's pretty, I think, common sense and pretty intuitive for that one. All right, so moving on to that first ionization energy. So the trend for that is actually as you go up, the ionization energy increases and also increases as you go to the right. So essentially going diagonally up to the right across the periodic table as your ionization energy is increasing. But why? Okay, and this generally goes back to size. So the smaller the atom, that means your electrons are closer to that nucleus. And that means that nucleus then has a tighter hold or pull on those electrons. A tighter pull or hold on those electrons means it's more difficult to take one away. Okay, remember that a higher number for your ionization energy, okay, means it's more difficult to pull that electron off. It becomes more difficult to pull the electron off when that hold that the nucleus has on it is very strong. And the hold that the nucleus has on it is related to both distance and strength of that nucleus. All right, and last up we have electronegativity or electron affinity. So either way. So this is one that also shows increasing going diagonally up to the right on the periodic table. The exception here, though, is your noble gases. Notice on this kind of 3D graph, your noble gases are flat. The electronegativity of noble gases is essentially zero. They don't bond, so they can't have an attraction to electrons and bonds if they don't bond with anybody. So we kind of ignore the noble gases a lot when we talk about the trends on the periodic table. So that's a good thing to kind of note or write down in your notes. The reason for this trend is pretty much the same as the reason for your ionization energy trend. Generally, that the smaller the atom, and we're going up to fluorine is one of the smallest atoms, the electrons are closer to the nucleus, and so the nucleus is more accessible and is actually just stronger. The other reason is because 8 is great, meaning all atoms want to have 8 valence electrons, right? They want to look like a noble gas with 8 valence electrons, or that full S&P shell. So the atoms that are very, very close to having 8 valence electrons want them so badly, want that one extra one so badly that they're going to do anything for it. And so that's another reason why our electronegativity is very high on the upper right corner of the periodic table. So let's summarize this. This is a great picture. This gives you both electronegativity and electron affinity, but it's showing the same thing. So you don't need to write both of those down. But I would maybe write that on the periodic table that we got that you guys have already colored in. The last thing I want to note on here is metallic character and non-metallic character. Okay, we know that metals over here generally on the periodic table. We know that nonmetals are generally over here on the periodic table, but we can also kind of think about as you go down to the left that metallic character increases. So francium is your most metallic. And if you think about it, we talked about how metals lose electrons, and the element with the lowest ionization energy, or the easiest to lose its electron, is francium. Okay, on the flip side, over here, we would have our most non-metallic, which would be fluorine, and that's because it gains electrons very, very easily. It has the highest electronegativity. So this kind of all goes together. So we're going to kind of summarize and practice with this in class tomorrow with some puzzles. That'll be kind of fun. So make sure to write this on your periodic table and come in with questions tomorrow.